and the heat transfer in a slab. A slab is basically a rectangular object which is easily represented in Cartesian coordinates. A slab can be a wall with flat surfaces. Okay. In this class, we'll continue the similar discussion, except we'll now move on to other geometries, other standard geometries. The two other standard geometries are cylinder and a sphere. So we'll take up a hollow cylinder and a hollow sphere and try to derive equations for estimating the temperature distribution inside and also the heat transferred when this particular cylinder is subjected to constant temperature conditions called as the Dirichlet conditions. Okay, so now let me share the slides. All right, so this is where we have stopped in the previous class. We have taken a plain wall and we have subjected to two constant temperature conditions. From this figure, you can see that Ts1 is the constant temperature on the left side and Ts2 is the constant temperature on the right side. And after deriving the temperature distribution, we see that see, you can, from the plot itself, you can see that this particular line is a straight line. That means the temperature distribution is basically linear. So the same behavior you can see from the equation also. You see Tx is the temperature at any x. So this equation represents the temperature at any point along the x direction. This is the x direction. So you can see here there are no terms involving squares of any quantity or cubes of any quantity or logarithms or exponentials or trigonometric ratios. Therefore, this equation is a linear equation. So the temperature distribution inside a plane wall is linear in nature. Another interesting thing that you can see here is that this temperature distribution does not have anywhere in its equation, it doesn't have the value of K. That means the temperature distribution is only a function of the end temperatures and also the distance and the thickness of the slab, not a function of the thermal conductivity. That means the material properties do not feature in the thermal distribution, in the temperature distribution. That's an important thing you need to remember. Also, we have not considered this convective conditions until now. These two convective conditions are not considered. We are only interested in deriving the temperature profile across this across this slab. We'll stick to the solid portions only. We'll bring about the convective conditions later on. Now we'll come to the cylindrical condition, cylindrical shape, especially a cylindrical shell. What is a cylindrical shell? Cylindrical shell is something which has a hollow space in it. That means you see here, this is the geometry you are seeing. So this is a cylindrical shell. So if you draw a solid cylinder, the cross section will look something like this. This is a solid cylinder. Cylindrical shell is something like this and this one. So typically a pipe carrying some fluid inside, or it could even be a vacuum. So that becomes the cylindrical shell. Now we will take up this cylindrical shell in this particular case and try to derive the equation of temperature distribution. Now you can see that this is a cylindrical shell, even though it looks elliptical. Imagine that this is cylindrical. It has got one inner radius R1 and outer radius R2. R2 minus R1 is the thickness of the wall of the cylinder. And also this inside surface has got, let us say, temperature T1, and the outside surface has got a temperature T2. Okay, so this is a long cylinder, and whenever we deal with this such a long objects, the amount of heat conducted along the length is negligible compared to the heat conducted across the length. So in this case, along the radius, the amount of heat conducted will be high, the thermal gradients will be high, and therefore there will be a temperature distribution along the radius, and practically the heat transferred along the length is 0. Okay, so you can see here this becomes a one-dimensional problem, one-dimensional conduction equation in one-dimensional steady state in cylindrical coordinates with no heat generation and a constant thermal conductivity. So for such a case, we have seen one general equation here. So in this equation, if you substitute n is equal to 1, so r power 1, so this is simply 1 by r. Similarly here r. So 1 by r dou by dou r of r k dou t by dou r. This is the conduction term in the solid part. Q dot is the heat generation term, and for the present case we are considering this will be 0, and it is a steady state, so dou t by dou tau will also be 0. So for this equation, we can, for this case we are considering, we can cancel these two terms. Is no generation and no transient. So only this one will remain, and even this, in this one, k is a constant. So k can be brought outside. Okay, so with all these operations, if you do, the ultimate equation will become dou by dou r of r dou t by dou r. Now the dependent variable is t and independent variable is r. Therefore, this equation can very well be written as d by dr of r dt by dr. That means the partial derivatives can be replaced by the ordinary derivatives because there is only one dependent variable. So this is the form of equation which we'll have to solve. Now you can see that if you see d by dr of dt by dr, so if you expand somewhere you will get d square t by dr square. Therefore, this is the second order equation. To solve this, you will need two boundary conditions. So we have given two boundary conditions. One boundary condition is the temperature at the inner radius, and another boundary condition is the temperature at the outer radius. So at r is equal to r1, t is equal to t1, and at r is equal to r2, t is equal to t2. So these are the boundary conditions we have. So with these boundary conditions, we have the required number of resources to solve this equation. So we will try to solve this or this differential equation. So solving a differential equation is we'll have to integrate it. So first time if you integrate, we can get rid of, if we integrate, once we will get rid of this term, only this will remain r dt by dr. So r dt by dr or r dou t by dou r, in this case dt by dr is more appropriate. That will be equal to, on the right hand you see it is, there is 0. Therefore, we will have one constant of integration c1, or we can write dou t by dou r is equal to c1 by r. Now this c1 by r cannot be written as a c2 because remember r is not a constant, r is a variable. It changes from r1 to r2. Therefore, we have to leave this right hand side term as a c1 by r1. So what we have here is a dt by dr is equal to c1 by r. So we have to integrate it once again using this variable separable method. So this is dt is equal to c1 dr by r. So we can integrate on both sides. C1 is constant, it will come outside. Integral dr by r is log r, natural logarithm of r. So using this, we can solve this. So you will get t on integration of dt, you have t, and integral c1 dr by r will be c1 logarithm of r, and then there is another constant of integration c2. So we have two constants of integration left here, c1 and c2. So we have to evaluate those and substitute in this equation to get the temperature distribution. So we will substitute this boundary conditions. So if in place of r, if I write r1, and in place of t, I can write t1. So I'll get one equation. Similarly, in place of r, I write r2, and in place of t, I write t2. I'll get a different equation. So I have two equations and two unknowns, c1 and c2, which can be solved for. So if you do that arithmetic, then you will have c1 as t2 minus t1 by log of r2 by r1, and c2 as t1 minus t2 minus t1 by log of r2 by r1 multiplied by r1, log of r1. So these two values, this value of c1 and c2, you can substitute in this equation. So if you do that, this will be the temperature distribution. This is the temperature distribution we are talking about. So you see the temperature at any radial location where R changes from R1 to R2. That will be equal to T2 minus T1 divided by log of R2 by R1. So this term is the value of C1, then log of R is there. The other one is the value of C2. So in this way, we can evaluate any temperature if we know the inner and outer radii and if we know the inner and outer temperatures inside a cylinder. Remember, we have not considered any fluid which is flowing inside. Okay, there may be some fluid flowing. We will see how to take care of that later on. Now, we may be very well interested in finding out what is the amount of heat transferred across this wall of the cylinder. We know that the wall of the cylinder is subjected to two different temperatures, inside T1 and outside T2. So there will be a heat transfer. What will be the heat transfer? Now the standard formula is the Fourier's law of heat conduction. So heat transferred inside a cylinder is again minus Ka dt by dx, but in this case the space dimension is the radial direction. So d in place of dt by dx we write dt by dr. Okay, because this is in the radial direction. So dt by dr is something we need here. Now you see here dt by dr we already have as C1 by R, where C1 is now this value. So substitute C1 here, we will have the value of dt by dr. So the same thing we have done, and you see here there is one equation available for heat transfer in a cylindrical shell. Remember, this is not a solid shell, this is a cylindrical shell. Similarly, we can do the same exercise. We can repeat the same exercise for a spherical shell. Spherical shells usually are used, spherical pressure vessels are used to contain fluids at temperatures which are different from the ambient temperature, especially in case of storage, some fuel storages, where spherical shape is one of the most compact shapes known to us. Given volume at the least surface area, which is very much good for heat transfer from the heat transfer viewpoint, because the area is least and therefore the heat transfer is also minimal. So in such a case of a spherical shell, how to estimate the temperature distribution and how to estimate the heat transfer? So for that again, we start with the conditions. We assume that it's a one-dimensional case, steady state, and we use the spherical coordinates because of convenience, and there is no heat generation, and also the conductivity is assumed to be constant. You see here, to try to solve one differential equation, so we have to get it into the simplest form, and to get it into the most simplest form, we have to make so many assumptions. So always keep an eye on the assumptions that you have made while deriving a certain equation. So the result of that solution will be applicable under the conditions in which the equation has been derived. So you should never lose sight of the conditions under which the equation has been derived. So like in the previous case, here also we have two temperatures. Inside is T1, outside is T2, and inside radius is R1, outside radius is R2. And the equation, the conduction equation is now like this. Earlier you see we had one R on the outside, now that R is in the inside. So how did we get this equation? Again, from this equation, if you substitute n is equal to 2, in place of n substitute 2, you get this equation. Okay, and you will have to remove this q dot and dou t by dou tau also. So you have this equation. Now, when you look at this, it appears to be a partial differential equation. But again, if you look at the dependent and independent variables, there is only one dependent variable and there is only one independent variable. T is the dependent variable which depends on R. Therefore, this is very well a ordinary differential equation which can be written as dt by dr multiplied by r square dt by dr is equal to 0. So now we have two boundary conditions, and like we did for the case of cylinder, we can also do for this. And you can see that on first integration, you will get rid of this outer term d by dr. What remains is r square dt by dr is equal to c1, or dt by dr is equal to c1 by r square. Then integrate it again, you will get, so if you integrate this again, you will get t is equal to integral c1 by r square dr plus a constant, a second constant. So now you have temperature distribution in terms of c1 and c2, which are the unknown constants. These values of c1 and c2 can be estimated if you substitute t1 in place of t and r1 in place of r. Likewise, if substitute t2 in place of t and r2 in place of r, you will get another equation in c1 and c2. So two unknowns, c1 and c2, two equations, it can be solved, and after solving it, you will get the values of c1 and c2 like you see here. Okay, now substitute these two values in this equation, and this is the temperature distribution that you get. So using this equation, at any R1 and R2, between R1 and R2, you can find the temperature at any point. Also, we may be interested in finding out what will be the heat transfer. So heat transferred is minus Ka dt by dr. Same Fourier's law of heat conduction. Area is now 4 pi r square. So for cylinder, what area did we take? 2 pi RL. This is the surface area. So this surface area is what we take, not the cross sectional area, it's the surface area. Likewise, in the case of a sphere, the surface area is 4 pi r square, and dt by dr is c1 by r square. So c1 by r square. Now we know the value of c1, so that substitute that, and you will get this expression for the heat transfer. Okay, so you can see once again that in the temperature distribution, thermal conductivity is absent, but in heat transfer, the thermal conductivity is present. That means the heat transfer depends on the end temperatures, thermal conductivity, and also the geometry. Whereas the temperature distribution does not depend on the thermal conductivity. So that is something you need to remember. Now, you can see these equations for the plane wall, you can see that this equation is a linear equation. So there are no squares, there are no logarithms, there are no trigonometric functions in this equation. Therefore, this is a linear equation, and you see when you plot it, it is a straight line like this. But in the case of a cylinder, you see here there is logarithm here in the temperature profile. Therefore, the temperature distribution will not be a straight line, it will be non-linear. So I have plotted that and I will show you. Similarly, in the case of a sphere, you see here we have R1 multiplied by R2. So we have some squares, some R square term is appearing here. So because of that, we will see that there will be non-linearity in the temperature distribution also. Okay, so I will show you that the temperature distribution now. You see here on the figure on the left, you have the temperature distribution inside a cylinder as well as the sphere. So I have taken the inner radius of the sphere as 5 millimeters and outer radius is 10 millimeters. Similarly for cylinder. And inside temperature, I have taken it as 100, outside temperature as 50. So these are the boundary conditions given. So once you have these boundary conditions, if you try to plot, you can see that this is not a straight line. These are some slightly curved. That means they are not linear. Whereas if you do the same for a slab, for the slab, the distance starts from x is equal to 0 to x is equal to 10. Okay. So for that, the inside temperature, I have given it as 100 and outer temperature as 50. So at any point inside the slab, you can find the temperature. And once you plot the temperature, you can see that this is basically a straight line. So for this Cartesian coordinates, inside the temperature, under the given conditions that we have derived, the temperature distribution will be linear, whereas for the cylinder and spherical coordinates, the temperature will be non-linear. So that is something you need to understand. Okay. Okay, now we'll move on to the next topic called as a thermal resistance and electrical analogy. Now this particular concept is used to take care of additional parameters like let us say inside this cylinder, if there is some gas flowing, so how to treat, how to evaluate the heat transfer and temperature distribution in such a case. So to have an easy solution for such problems, just remember, if you want convection also here, then your boundary conditions will change and it will be difficult to solve this equation. So for that, this electrical analogy and the concept of thermal resistance will be useful. So just look at this particular figure. This is the same figure that we have seen in the case of the Cartesian coordinates. It's a slab. So it's a slab having wall temperature, inside wall temperature as Ts1 and outside wall temperature as Ts2, and the temperature profile is shown here as a function of x. Additionally, you also have convective environment on the inside and convective environment on the outside. Okay, so how to treat this problem and how to evaluate things much easier. So for that we have this electrical analogy. Okay, before we go there, I'll just refer you to the temperature distributions you see here. No, I'll just write it down here in the data book. I hope all of you have purchased the data book. Temperature distribution is available in the page 52, page 53, page 53. So you have the equations for temperature distribution. You also have the equation on top of page 52. If you open this book and see on top of page 52, you will see it is written as Q is equal to delta T overall divided by R. R is the thermal resistance. So in this way, we can also represent the heat transfer. Okay, now you see here in this equation, Q dot, this is nothing but Q dot. Q dot is equal to 4 pi k R1 R2 divided by R2 minus R1. So that means that this term is something related to the R. What else is remaining? The overall temperature distribution, T1 minus T2. This is this one. So T1 minus T2 divided by this term, if we take it down, it becomes inverse. So in that way, we can say that this term is equal to R. So this is called as the electrical analogy and the thermal resistance concept. We'll see how this works. Now you see here again, coming back to the slab, the heat transfer inside the slab is given using the Fourier's law of heat conduction. Q dot x is equal to minus Ka dt by dx, very standard equation. dt in this case inside this inside the slab is Ts1 minus Ts2. So I am getting rid of this negative symbol. If I want to keep the negative symbol, I will have to write it as a Ts2 minus Ts1. So I have got myself written off that negative symbol so that I deal with only positive quantities. So Ts1 minus Ts2 divided by L. So there is nothing wrong in writing this because now we know what is the phenomena, what is the significance of this negative sign. Now you bring this Ka here. So Ka here, this will become L by Ka. So Ts1 minus Ts2 divided by L by Ka. Now you imagine Q is heat flowing. Ts1 minus 2 is some kind of a temperature difference, some kind of a difference which is driving the heat transfer, and L by Ka can be looked at as the resistance. So if you look at this equation and you see this equation which you are familiar with, I is equal to V by R. So Q is I. V, which is the potential difference, is similar to the temperature difference, and R, which is the resistance, is equal to or similar to the thermal resistance. So I is similar to Q, V is similar to the temperature difference, and R is the thermal resistance. So like this, you can write that because R is equal to L by Ka, we write it as a R thermal. R stands for resistance, T for thermal, and for conduction, COND for conduction. Now we have to be specific because we are talking about the resistance inside the wall, and inside the wall there is only conduction resistance. Okay. Now this is what is called as the electrical analogy. So we are relating heat transfer to electric current. So heat transfer is a flow of some thermal energy. Electric current is also flow of some electrical energy. You can explain in terms of electrons, but let us not go so deep. For us, the superficial understanding is sufficient. Now, what is driving the heat transfer? Thermal difference is driving the heat transfer, or thermal gradient is driving the heat transfer. What is driving the current? Potential difference, voltage difference is driving the current. And what determines how much current or how much heat will flow? How much heat will flow will depend on the thermal resistance, and how much current will flow will be determined by the electrical resistance. So thermal and electrical resistance are similar. So in this way, we are trying to make heat transfer and electrical or current flow analogous. So in that way, we could come up with the resistance, thermal resistance in the conduction, it is equal to L by Ka. Similarly, if you take this entire situation, you have some convection environment here, and heat has to flow from this point to this point. So from the fluid to the surface. So here also there is heat transfer. Here also there is a temperature difference. Therefore, here also there will be some kind of a resistance. But this resistance will not be conduction resistance, it will be convection resistance. Similarly, on the other side, there is a fluid, therefore there will be some convection resistance. So how to account for convection resistance? Now let us write the convection heat transfer equation, the Newton's law of cooling. It is a Q convection, the heat convected is equal to HA multiplied by Ts minus T infinity. Ts is this surface temperature, T infinity is this temperature. In fact, this heat transfer takes place from here to here if this is the high temperature. Okay, but let us not go into those details. So you can see here, convected heat is HA multiplied by delta T, some thermal gradient. So if you bring HA to the denominator, it will be thermal gradient divided by 1 by HA. So according to the electrical analogy, convected heat is, if this is equal to the current, the potential difference is equal to the temperature difference, then the electrical resistance should be equivalent to the thermal resistance. So R is equal to 1 by HA. So whenever we have convection, the resistance is 1 by HA. That is in convection conditions. So you see here the convection resistance is written as R with a subscript T. So resistance T for thermal, but because of convection. So because of conduction, L by Ka. Because of convection, 1 by HA. Okay. Now let us look at the entire schematic that we have here. Got all these things. Now let us look at the entire schematic here. We have heat flowing from this end to this end. T infinity, Ts1, Ts2. So totally this is the direction of heat flowing, and for the heat to flow, it has to overcome the convection resistance, overcome the conduction resistance, and there is a convection resistance again. So you can see there are three resistances connected in series, one after the other. So this is represented as the electrical analogy or the electrical network. So you can see here, this convective resistance is represented by this symbol. Conduction resistance is represented by this symbol. And the outside convection resistance is represented by this symbol. So convection resistance we know is 1 by HA. In this case, H1, H is H1, so 1 by H1A. A remains constant because this is a slab, so inside area and outside area are the same. But for cylinder and sphere, they will be different. Similarly, for the conduction resistance, this is the quantity, and L by Ka will be the term we'll be using to evaluate. So L by Ka, we have seen this here, so that's what we use here. Similarly, outside convection resistance is 1 by H2A because H2 is the convection coefficient here. So altogether, the total resistance will be, we know from electrical analogy, the sum of the resistances connected in series is the sum of each resistance, individual resistance. So 1 by H1A plus L by Ka plus 1 by H2A. That will give the total resistance. So if you want to evaluate the heat transfer across this, we will have to write it as Q is equal to delta T overall divided by R total. So this will be, for this case, if I want to write, I can write it as a T infinity 1 minus T infinity 2 divided by R total. So in this way, I can calculate the heat transfer for this case. So this is the way in which we use electrical analogy, and it's a simple approach. Even though many assumptions have been taking place in this, it's a simple approach. But the advantage of that is many complex problems can be solved. So the recent application of this electrical network or electrical analogy has been used in finding out the temperature distribution in electric motors. You know, in electric motors, there is a stator, there is a rotor, there are magnets, and there are so many resistances inside. All these things, some of them are connected in series, some of them are connected in parallel thermally. So we can represent the electric motor itself as a network of thermal resistances, and we can evaluate what is the total thermal resistance, and we can also evaluate what is the temperature distribution at different points. So that becomes an easy way of approaching a complex problem. So for such applications, this network thermal resistance and electrical analogy concept has been used. Similarly, if you have the radiation, so radiation can be written as H, radiation heat transfer coefficient, multiplied by the area multiplied by Ts minus T surrounding. Remember, this is not the basic way of estimating the heat transfer coefficient. So this is one way of treating radiation similar to convection. So where we get this radiation heat transfer coefficient, and earlier we have seen how to estimate the radiation heat transfer coefficient. You see here, this equation is used to estimate this radiation heat transfer coefficient. So you can see that even for radiation, if we treat it as convection, then we have this radiation heat transfer coefficient, and the resistance will be 1 by HA. But where H is the radiation heat transfer coefficient. So the radiation heat transfer may be important if the convective heat transfer coefficient is small. So there are situations where radiation heat transfer is to be considered. For example, when the temperatures are high or when the convection coefficient is low, then radiation becomes important. Surface radiation and convective resistance act in parallel. So you will see this, what is parallel and what is series. We just seen what is series. You'll also see what is parallel. So surface radiation and the convective resistances, they don't act in series, but they act in parallel because they're happening together from the same surface. Okay. Now coming to the concept of this composite walls. So what are these composite walls? Until now, we have seen only one slab having only one material where it has got the thermal conductivity K. But let us say this is the wall of a building. Wall of a building, the core is made out of bricks, and the left side and right side are plastered with cement. So that means this particular wall, actually in reality, it is actually made out of three surfaces. One cement surface, then the brick, and again the wall. And bricks also, you see, the bricks, they will not be, all of them are not connected in series. Some of them are also connected in parallel. So this particular wall may be 2 brick thick, but at the same time, at the bottom of each brick layer, there will be another layer of brick. That means inside the bricks are connected in series and also connected in parallel. So you can see that the walls involving any number of series and parallel thermal resistances due to layers of different materials. So in the example that I gave you, the different materials are cement and brick. So you see here, if there is only one brick layer and there is one layer of cement and another layer of cement, we will get this kind of a system distribution where everything is in series. But if you have different bricks connected in parallel also, then you see here, there is a layer of cement, 2 bricks connected in parallel, and then there is a layer of another cement. So this is a purely series network, and this is a combination of series and parallel networks. So in this way, we have what are called as the composite wall. So composite wall is nothing but like a sandwich, different materials kept together closely. which makes a composite wall here. Okay. Now let us take the case of the composite wall in series. So if we have three walls, in this case only three are considered, three solid walls, and there is a convection environment on the left side or inside and the convection environment on the right side. Therefore, if such is the case, how to treat this? So when we say how to treat in heat transfer, we will always be interested in finding out two quantities in heat transfer. One is what is the heat transferred. That means how many watts of heat has been transferred. The second important question is what is the temperature distribution. So these two questions are important in heat transfer. A third question may also be important. You may be asked what is the heat flux? Not just heat transfer, what is the heat flux? Heat flux is heat transfer divided by the area. So that's the third question, but not important at this point of time. So if we have such a situation, if we have three layers of solid materials and on the outside and inside we have convective environment, this is one case of a composite wall and how to evaluate its thermal, its heat transfer. So for that, we will take the concept of, now remember, do you remember the concept of pipes in series and pipes in parallel in case of fluid mechanics? In flow through pipes chapter, you have seen pipes connected in series and pipes connected in parallel. In pipes connected in series, the amount of fluid flowing in the first pipe is same as the amount of fluid flowing in the last pipe. That means in pipes connected in series, the flow rate is the same, but the pressure drop in different pipes will be different depending on the diameter of the pipe, length of the pipe, and the surface finish of the pipe. Likewise, if we have pipes connected in parallel, we will have different flow rates in different pipes, but the pressure drop in each pipe will be the same. So in pipes in series, the heat transfer, the flow rate will be the same, pressure drop will be different in each pipe, whereas in pipes connected in parallel, the pressure drop will be same in each pipe, but the flow rate in each pipe will be different. So that's the difference between pipes connected in series and pipes connected in parallel. Similarly, when we come to composite walls, when we have solids connected in series, what happens is the amount of heat transferred through each quantity is the same. That means heat transferred from this fluid to this wall is same as heat transfer from this wall to the second wall, from here to here, from here to here, and from here to here. So heat transfer remains the same, but the temperature drop, you see here, this temperature drop, which is parallel, which is equivalent to the pressure drop in case of fluid flow, that will be different. So here you see the temperature drop is low, but here the temperature drop is very high, and here again the temperature drop is low. So depending on the thermal conductivity and the thickness, the temperature drop will change. Now keep that in mind. Now we will have to find out what is the heat transferred and what is the temperature distribution in each of these cases. So we will use the concept of electrical resistance network. So we know that there is a convection here, so there will be convection resistance. In the first slab, conduction resistance, second slab, conduction resistance, third slab, conduction resistance, and outside there is a convection resistance. So we have 2 convection resistances and 3 conduction resistances. So totally 5 resistances. All of them, fortunately for us, are connected in series. So in such a case, what we do, we will create an electrical network of resistances. So you see here, the temperature of this fluid is T infinity. So that is the one extreme temperature on the left hand side. So this node is represented as temperature T infinity, and the surface, this surface is represented with the temperature is TS1. So this is TS1. This node is TS1. The next one is T2. So this temperature is T2. The next one is T3. The last surface is TS4. So this one. And the final fluid temperature on the other extreme is T infinity 4. So we first mark all these temperatures from the inside to outside. So this is the inside, let us say, and this is the outside. These are all the temperatures involved. And now we will connect these temperatures with the resistances. So first we have convection resistance here. Convection resistance formula is 1 by HA. So you see 1 by HA. So H1 is the heat transfer coefficient. So This is 1 by H1A. Then we have this conduction resistance. Conduction resistance is L by Ka. L is the thickness, K is the conductivity, and A is the surface area. In this particular example, the surface area for convection on the inside and outside, and also the surface area for conduction inside in these surfaces, it's all the same, fortunately, because this is a slab. So A is the surface area. Conduction resistance for this surface, for this slab is L by Ka. Similarly, for this slab, the second slab is LB by KBA. The third one is LC divided by KCA. And finally, the last convection resistance is 1 by H4A. So all these now are connected in series. So 1 by H1A, LA by KA, LB by KBA, LC by KCA, 1 by H4A. All of them are connected in series. Now, as I said, the heat transferred from here to here should be same as the heat transfer from here to here, here to here, because the whatever is entering should leave. So heat transfer is the same, but the temperature drop will be different. Now, how to calculate the heat transfer? So you have this equation Q. You start with Qx. Qx is equal to heat transferred. Let us say heat transferred in the first across the first resistance. First resistance is this convection resistance. So that is written as T infinity 1 minus Ts1. See this T infinity 1 minus Ts1 divided by the convection resistance 1 by H1A. The heat transferred in the second resistance will be, because of conduction resistance, it will be temperature difference Ts1 minus T2. Ts1 minus T2 divided by the conduction resistance, which is LA Ka by A. Similarly, in the next slab, we have temperature difference is T2 minus T3 divided by LB by KBA. Then T3 minus TS4. T3 minus TS4 LC by KCA. And finally, from this surface to the convective environment, TS4 minus T infinity 4 divided by 1 by H4A. So each of these quantities will be equal to Qx. Okay, now from this we'll have to evaluate Qx. How we can do is, you take the first equation. You can write it as T infinity 1 minus Ts1 is equal to 1 by H1A multiplied by Qx. Similarly, take the second equation. You can write it as Ts1 minus T2 is equal to LA by KA Qx. From the third equation, you can write it as T2 minus T3 is equal to LB divided by KBA Qx. Likewise, you can write it for fourth equation and the fifth equation. Now, what happens is, if you will have like this, you will, like I have written 3, you will have 2 more. So totally it will be 5. So for all this, you add the left hand side. If you add the left hand side, what happens? You just observe the first 2, T infinity 1 minus Ts1 plus Ts1 minus Ts2. If you add these 2, this and this gets cancelled, and what remains is T infinity 1 minus Ts2. This, if you add again to this 3, minus T2 will cancel T2. So what happens is, if you add all these 5 equations, the left hand side as well as the right hand side, what happens is you will have T infinity 1 minus T infinity 4. This one T infinity 4 on the left hand side, and on the right hand side you will have Qx multiplied by all these resistances together, 1 by H1A1, this one, this one, this one, this one together, all this one. Okay, so from that you can write Qx as T infinity 1 minus T infinity 4 divided by this. So that is what is written here. So I hope you understood how we got this equation. We have to add all this so that you get so that this intermediate temperatures will get cancelled. Only the extreme temperatures, only T infinity 1 and T infinity 4 will remain. So here T infinity 1 minus, this is not T infinity 2, this is T infinity 4. So extreme temperature, or it's also called as the overall temperature difference divided by the total resistance. Okay, so this is the general equation for the heat transfer. Now you see what's the difference between the heat transfer equations that we have derived here. Here the heat transfer is only across the solid wall, only one resistance. So this is the thermal resistance. Whereas in this case, we have 5 resistance. We have different solids and also we have different environments. So 5 resistance have been considered and all of them were used to find out the net heat transfer across this particular composite wall, which is connected in series. So in this way, you can evaluate the value of heat transfer. Now that will be one question. As I said, in any heat transfer problem, 2 questions. One will be what is the amount of heat transferred, and another one will be what will be the temperature at a particular location. Now, how to find the temperature at any location? What you can do is, you see here, use this equation to calculate Qx, and then come to individual heat transfers in this one or this one, this one, this one or this one. I will just give you the example of this one. Here, you may be knowing T infinity 1. You just knew Qx. So you also know H1 and A. So the unknown Ts1, that is the surface temperature of this wall, can be calculated. Similarly, now since you know Ts1, use that equation here to calculate Ts2. Likewise, use T2 here to calculate the value of T3. So in this way, you will be able to find out the temperature at different locations. But using this resistance network, you will be able to find the temperatures only at the boundaries. Okay, that you must keep in mind. So this is one example of a composite wall which is in series. Now what will happen if something is in parallel? Now you see here, this is parallel, 2 surfaces having 2 different conductivities, and each surface on the left hand side is subject to a temperature of T1. So this entire surface is T1, this entire surface is T2, but here the conductivities are different. So these 2 different materials are not connected in series, but they are connected in parallel. So you can represent this as like this. So T1 is the node of the first node, T2 is the last node, and you can see the resistance offered by this upper material is represented as R1, and the resistance offered by the lower material is represented as R2. So now you see there is different heat transfers flowing in the 2 resistances, Q1 in this, Q2 in this, but Q1 plus Q2 should be equal to Q. So total energy entering at this end should be same as the energy entering and energy leaving from the other end. But intermediately, because the resistances are in parallel, you have different amounts of flow rates. So what you need to do is, again, we know from electrical technology, we know what will be the net resistance when 2 resistances are connected in parallel. So this is the formula. The total resistance, 1 by total resistance is equal to 1 by R1 plus 1 by R2. So inverse of the individual resistances summed up, that will give you the total resistance. So in this way, you can evaluate the total resistance, and the heat transfer will be T1 minus T2. That is the overall temperature difference divided by the total resistance. So in this way, you can evaluate the value of Q. Okay. So do you understand this? So we have seen materials in series and materials in parallel. Now you may have situations where there are things in series and as well as in parallel. So here you see we have one material. Second and third materials are connected in parallel, but in turn they are connected in series to the left material and also the right material. So what in such cases, what you can do is you represent this resistance like this, and this resistance and this resistances as 2 resistances connected in parallel, and the last one here. Now you can find out the net resistance of these 2 parallel and then come up with one single series resistance and then evaluate as usual. So that is how we can do it. Or there is another way also proposed here. I suggest you go through this and you will understand this. Similarly, here you see there are 2 resistances connected in parallel and the last one is connected in series. So this one is represented as this resistance, this one is represented as this resistance in parallel, and this one in series. So you can combine these two, and the resulting one can be combined with these ones. So in this way you can simplify. In fact, maybe in the next class I will show you how an electric motor is whose temperature distribution is evaluated by using a series and parallel connections of resistances. Now we'll stop here. I think time is up. We'll stop here and continue in the next class. But if you have any questions, maybe I'll be able to take a couple of questions before I take your attendance. We'll solve some problems. Probably, we have about 10 classes more before CAT 1. So the next 2 classes, I will deal with theory, and then I'll take up problems. So heat transfer is a subject which you will have a better understanding if you go through the problems. Okay. All right, I'll stop the recording.